Anyone have any questions? All right. So just a couple comments on this. And I just want to remind everyone, I want to keep going back to these approximations we've made, because I'm going to spend very little time talking about what happens when we relax those approximations. But those are critical, the approximation of linearity and the approximation of homogeneous flow. Because really what I'm giving you first here is an idea of, if you have a disturbance in a Newtonian fluid, in essence, a perfect gas Newtonian fluid, how does that disturbance propagate? But I'm not telling you about where those disturbances come from, what creates them, what amplifies them. And to understand that, you have to include effects of nonlinearity, effects of inhomogeneity, et cetera. But this just tells you, once they're created, what happens to, how do they move around? But I'm not addressing the question of how are they created. I'll try to tackle that just briefly before we wrap this stuff up. But just to make a couple comments. So in a homogeneous uniform flow, these three disturbance modes, they propagate independently. And again, approximations matter, because the moment I allow for nonlinearity, the moment I allow for spatial gradients in quantities, or as I watch these disturbances move through the flame, they'll start to couple with each other. But they don't couple in a, if you just say, okay, post-flame, let's just say you assume that after the flame, I've got all these, the flames are great sources of disturbances. They make sound waves, they make entropy fluctuations, they make vorticity. All this stuff is just shedding out of the flame. What happens to it post-flame, between the flame and the exit of the combustor? It's a good mental model. And when I say they propagate independently, what I mean is that second bullet is they're decoupled. So you got vortical disturbances, you got acoustic disturbances. They both induce flow motion. So if you want to know what the velocity is doing, you have to know what the vorticity and the acoustic field is doing. But the vorticity and acoustic fields are independent of each other. They don't talk to each other within the approximations of this. So in other words, fluid rotation and fluid volume fluctuations do not interact with each other. And then lastly, the disturbances, remember we had that AP and BP and AS and A omega. And all those disturbances have constant amplitude. They're moving upstream with the speed of sound. They're moving downstream with the speed of sound. They're propagating with the flow, constant amplitude. So there's no sources or sinks. So again, you have to have boundary conditions, or you have to know something about, it's not telling you where these disturbances come from. Once you create them, they have constant amplitude. A couple other comments. So as we mentioned, acoustic disturbances propagate at the speed of sound. Entropy and vortical disturbances propagate with the flow. So what that means is there's very different length scales over which these things vary. So, and this has a lot of implications for a number of combustion problems. So for example, acoustic. You're very familiar with the concept of an acoustic wavelength, right? So if you have a harmonically oscillating acoustic disturbance, it's moving at the speed of sound. It repeats itself over a periodic wavelength, which I'll call lambda sub whatever this is, capital lambda. And that's the speed of sound divided by frequency, right? Now, if I have a harmonically oscillating vorticity disturbance, it also has a wavelength that repeats itself over a spatial interval. But it's not moving as fast. It's moving, at least if it's a subsonic flow, it's moving at the speed of the velocity. And so its wavelength is what we sometimes call a convective wavelength. All right? And that's U naught over F. So just speed of propagation. In one case, it's C. In the other case, oh, you can't see my mouse. Nuts. In one case, it's C. In the other case, it's U. And so what that means is, in a disturbance field where all these things are coexisting, the entropy and vortical mode wavelength is shorter. And in a low Mach number flow, it's a lot shorter than the acoustic by the Mach number, right? So if you just take a ratio of these length scales, that's U naught on C naught, that's the Mach number. So Mach number of 0.05, for instance, that means the acoustic disturbance is 20 times longer than the vortical disturbance. And so, I'll talk about that later. But this has important implications, for example, in how, velocity fluctuations interact with flames. So, I showed you those images of that from Sebastian Kandel's group of fluctuating flow field. You can see the wrinkles on the flame. Well, all velocity fluctuations are not equal in terms of how flames respond to them. Because if the velocity fluctuation comes from a vortical disturbance, the the vertical disturbance has a much shorter wavelength than the acoustic disturbance. And it turns out that that wavelength or that speed of propagation has a huge impact on what the flame sensitivity is to it. In fact, we're going to spend most of the rest of today talking about that. And so you can have the same velocity fluctuation. You can have fundamentally different flame response, Q prime, where Q would be your heat release, depending upon whether that comes from an acoustic wave or a vertical wave. A few other comments is that acoustic disturbances, we call these all waves, but in reality, my own working definition of a wave is a disturbance that propagates information and energy without propagating mass. So those of you in the back of the room, you can hear me, even though the molecules in front of my mouth are not actually physically going over to you, right? That's what acoustic waves do. They propagate energy and information. Whereas acoustic and vertical, the only way that energy is getting from here to you is if someone's physically carrying it. But those acoustic waves, and they do all the things that waves do, right? They diffract, they refract, they reflect, etc. So if one of you were sitting around the corner, and even though you couldn't see me, you could still probably hear me because sound waves bend around things, right? These walls, sound waves are hitting them, and they're bouncing off of them. When sound waves interact with changes in speed of sound, like flames, here's a fun little image of an acoustic wave hitting a turbulent flame, that change in speed of sound refracts the sound wave. Just like when you look in your fish in a pond or in an aquarium, you put your hand in there, your hand bends, and that's refraction because the speed of light changes. So that's what acoustic waves do. Whereas acoustic and vertical disturbances, they go with the flow, right? We haven't talked about diffusion, but really the only way that they can move from a region where the flow isn't taking them is through the action of diffusion, which in a high Reynolds number flow is pretty slow. So the only way an acoustic or entropy disturbance affects another part of the flow is if the flow physically carries it there. And just to illustrate that, here's some just to demonstrate some of this point about these coexistence of these disturbances. I'm going to show you some data. This is data taken by Jackie O'Connor. She's a professor at Penn State. And flows going left to right. You have this annular nozzle. We talked about annular nozzles yesterday and why we do those. And I have this transverse acoustic wave going up and down. And so that transverse wave is exciting fluid motion up and down. But it also, because acoustic waves refract, propagates into that nozzle. So that's that refracted acoustic wave. So it also induces axial motion. And by the way, there's a word for this. It's sometimes called injector coupling in, like, for example, the rocket literature. Because when you had combustion instabilities in rockets, you'd have these transverse acoustic waves, but they would induce modulation of mass flow rate of the fuel and oxidizer. And it's basically an acoustic refraction problem, is that these sound waves are bending. But they're also, we'll talk about this in a minute, they're exciting vertical disturbances. You have flow, so you have a separating shear layer here and here and here and here. And so the resultant disturbance field is now, what started it all was Jackie excited this transverse wave, which is just acoustic compressional dilatational disturbances moving at the speed of sound, going up and down, but it also excited these acoustic dilatational compressional disturbances moving this way, and it actually also excited, which you don't have the background yet to understand why, but I'll explain to you in 10 minutes. It also excited vertical disturbances, and those are convecting rotational disturbances. And in fact, if you were to say, to look at what is the velocity fluctuations along a line here, all right? This is data showing you the magnitude of the symbols or the velocity fluctuations along that line. I just jumped forward 2 slides. This is the phase of those velocity oscillations. Okay? So what this means is, hey, if you're sitting right here at, whatever it is 0.6 by the way, lambda c is convective wavelength. So if you're sitting 0.6 convective wavelengths down from the exit of the nozzle coming into your combustion chamber, the oscillations are pretty small, whereas if you go just a little bit downstream at 1, they're about almost 3 times larger. In fact, they have kind of this periodic pattern. What's going on here? And this is not an acoustic wavelength. Well, in order to explain this, let me just do a simple little model problem for you to say, what does the disturbance field look like if you have 2 disturbances at the same time but moving at different phase speeds, right? So if any of you have ever taken like a physics class, even your high school physics class, you're probably familiar with standing waves, which is what happens when you have 2 waves going in opposite directions. That gives you these standing waves. Here, I don't want to think about 2 waves moving in opposite directions. Here, I want to think about 2 waves moving in the same direction but at different speeds. Okay? So let's assume that I have an acoustic wave and a vortical wave moving in the same direction. One has a amplitude of a lambda. It's moving at a speed of sound. The other is moving at the flow velocity. They're both moving in the same direction. That's the minus. That's the minus. And just for simplicity, let's assume that the amplitudes of that acoustic and vortical disturbances are the same. And you can use some trig identities to get this would be what the velocity that you'd measure. Because remember, the velocity is the superposition of this thing. And what's interesting is this is a disturbance that has constant amplitude. This is a disturbance that has constant amplitude. So the amplitude of this thing doesn't change in space. Its phase does. But if you took a velocity, if you took PIV measurements, you'd see the same amplitude of velocity fluctuations at every point as down x. The phase would be different, but not the amplitude. But now if you look at the superposition, okay, here's that you can see some space-time coupling. But this is the amplitude. It's this whole thing. This thing does vary with space. So the velocity field, the magnitude, you take 2 constant amplitude waves, you allow them to interact with each other, and you get actually a disturbance field whose amplitude changes in space as that. And that's actually what's happening in that data there. So I just took that same simple model, and it turns out that, and I determined what the amplitude of the acoustic and vortical disturbance had to be, and it turns out that ratio 0.6 gives you this line. That's that fit. So in other words, if you had a way to measure only the amplitude of the acoustic wave, it has constant amplitude. It doesn't change in space. You could measure only the vortical disturbance. It doesn't change in space. Their superposition does. And in fact, if you look at the data, it really nails the phase in particular. That's clearly what's going on here. So this is a nice, like I said, this is an understanding that in real complex flows, you have these 3 canonical disturbances. It gives you a great mental model to make sense of complicated experimental data or complicated computations. All right, so now I want to say this is like, it kills me to only have 1 slide to talk about this stuff, because now I want to relax all those assumptions that I made about homogeneity and linearity, because that's where the rubber hits the road. That's what makes life really interesting. So we've just talked about what happens to small amplitude canonical disturbances. We've shown that you have these 3 canonical disturbances modes. And we've shown that they propagate independently of each other if they're really small amplitude and the flow is inhomogeneous. But in reality, that's not the world we live in, right? And so what happens is they start to interact with each other, and they also you get sources and sinks of these disturbance modes through 3 processes. One process is at boundaries. So we haven't talked about boundary conditions at all. But for example, when an acoustic wave hits a wall, it can actually excite vortical and entropy disturbances. Why is that? Well, it's because when sound waves hit a wall, how many of you have taken an acoustics class? Okay, so when a sound wave hits a wall at an angle, it excites a reflected wave that reflects at equal and opposite angle, equal angle. And the reason it does that is because basically the way you can figure that out is the sum of the incident and reflected wave give you 0 normal velocity at the wall. So that comes from the wall boundary condition that the normal velocity at the wall has to be 0. So in essence, what you have is, you can imagine you got a wave going this way, and that reflected wave, the normal velocity components are equal and opposite amplitude, and they give you 0. But they have the same tangential direction, right? That incident and reflected wave both excite velocity fluctuations at the wall in the same tangential direction. And if you have a no-slip boundary condition at a wall, you need that reflected acoustic wave isn't going to satisfy that boundary condition. So it actually takes a vortical disturbance that is excited at the wall as well. So when a wave hits a wall at an angle, it excites a reflected acoustic wave, but it also excites a vorticity disturbance. And so remember I mentioned to you that not all kinetic energy is equal. An acoustic wave is this compressional velocity disturbance. A vortical wave is rotational. So what the wall actually does is it acts as a mechanism for transferring one form of kinetic energy into another form of kinetic energy. You can't, in the free space, it doesn't happen. There's no mechanism for that to happen. Once that kinetic energy is dilatational, it stays dilatational. It can't get converted into rotational. But it hits a wall, the wall partially converts some of that dilatational kinetic energy into rotational kinetic energy. So that's that one. It also, so an acoustic wave hitting a wall excites vorticity. It actually also excites entropy disturbances because you also have a thermal boundary condition at the wall. Let's suppose, if your wall has a much larger thermal mass and the temperature of the wall is not fluctuating, but the temperature of the acoustic wave is fluctuating, the only way you can satisfy that boundary condition of no temperature fluctuation is to excite an entropy disturbance. So bottom line is sound wave hits a wall, it excites a reflected acoustic wave, a vortical disturbance, and an entropy disturbance. And so what that manifests itself is that reflected acoustic wave actually has less energy than the incident wave because some of the energy got rearranged. So that wall provides a means for moving energy around between these disturbance modes. Again, these disturbance modes are independent in the free space stream. They don't talk to each other. They don't interact. You got energy in the acoustic wave, the vortical wave, the entropy wave. And whatever's there is there. But when they hit the wall, energy starts reshuffling between them. And in this case, people in acoustics call it acoustic damping when a sound wave hits a wall. But really what's happening is there's not damping of energy, it's just rearrangement of energy. Energy is moving around from one form of energy to another form of energy, disturbance energy. Okay, so that's one way. The other way is regions of flow inhomogeneity. So where does flow inhomogeneity show up? Well, the big one in combustion is temperature, right? You get these massive temperature gradients in flows. You get pressure gradients in flows. You get density gradients in flows and so forth. And it turns out that those gradients are also ways in which these modes couple. So for example, as a vorticity disturbance, or turbulence basically, propagates through a flame, that temperature jump across the flame rearranges, it takes some of that energy out of that vortical disturbance and it plops it into an acoustic wave that goes zinging off at the speed of sound and an entropy disturbance, which is convecting downstream. Or similarly, when a sound wave hits a flame, dilatational, the flame converts some of that energy into vorticity. So you get this convecting vortical disturbance. So flames, when these disturbances interact with flames, the flame scrambles it all up. It moves energy around between these different disturbance modes. And there's some really cool papers out there in the literature where people quantify how energy moves around as one type of disturbance energy interacts with a flame. The second bullet here, is anybody working on combustion noise problems here? Okay, so this second example is actually a really current example right now because jet engines, historically, the dominant source of noise comes from what we call jet noise, which is high velocity turbulent fluctuations, which we talked about earlier. Well, aircraft engines now are going to such high bypass ratio that jet noise is dropping, and so it's no longer the high velocity jet outside the engine, it's what we call core noise. It's the stuff inside the jet engine that's starting to become dominant. And that's the spinning turbine and the combustor. And so all of a sudden, a problem I've worked on in 20 years has gotten really hot, which is combustion noise, because jet noise is dropping. And so how does the combustion process make noise that, when a plane flies overhead that you hear? There's really two mechanisms. One is what we call direct sound generation, which is the rate of heat release from the flame generates sound waves. So the flame is a source of acoustic waves. And in one way that is actually is you have a turbulent flow. As that turbulence propagates through the flame, that the flame converts some of that energy in that turbulence into acoustic waves that then go flying out downstream and propagate everywhere. But there's also that's called direct noise. But there's also indirect noise. And indirect noise is really interesting, and you can only understand it from what we've talked about today. And that is, if you have an entropy disturbance and you convect it through a nozzle, you make sound. All right? So, and flames are big-time entropy disturbances. And by the way, the reason for that is it all goes back to F equals ma. If you think about a nozzle, what does a nozzle do? It accelerates a flow. How do you accelerate a flow? You got to have a pressure gradient, right? That's the momentum equation. Force equals mass times acceleration. How do you get force? You have a pressure gradient. So if you have a fluid with a fluctuating density, which we know that density disturbances come from entropy disturbances, then the force required to accelerate that fluctuating density through the nozzle is oscillatory. You follow me? So so if I have a fluid with a given density, and I'm running it through a nozzle with a given area change, it requires a certain pressure gradient across that nozzle to accelerate that density, right? But suppose I give you an oscillatory density that's going through the nozzle. That's going to require an oscillatory pressure gradient. It's just because the density, it's rho times du dt is going to be the pressure gradient. And so what we have then is, and that pressure gradient means, remember, what is pressure? Pressure is one and the same with acoustic waves. And so what that means then is flames are sources of entropy fluctuations. And if the flow was just convecting out with any change in speed, those entropy disturbances would just get washed out into the environment and they would diffuse away. But if you run them through a nozzle, like you would have in a propulsion system, those entropy disturbances create acoustic disturbances which propagate away. That's indirect noise. So a very interesting topic that people are arguing about right now is what is the relative contributions of direct noise versus indirect noise, because because the fix for them is different. One is fluctuations in heat release directly making sound. The other is the sound in the combustion chamber. The other is the entropy that the flame makes interacting with the nozzle that makes sound. Okay. Okay, so that's regions of flow inhomogeneity. The last source of coupling or sources of disturbance modes is through nonlinearities. So I gave you that little trick question before. You may remember the trick question I asked you before, which was, I said, how in the world is this thing zero, P1 omega 0? And you can go to the lab, take a turbulent jet, you can stick a pressure sensor, and you'll measure all kinds of pressure fluctuations that turbulence generates. But that's enough. You can't understand that from linearizing the equations. You got to include nonlinearities. And so, in other words, vortical disturbances do make sound. They just make it at second order. You got to include nonlinear terms. And the reason for that is that, again, just to use this as an example, this is not an aeroacoustics class, but vortical disturbances, remember, they're rotational disturbances. They're not dilatational disturbances. And it's really hard for just pure fluid rotation to change the volume of the fluid. But if you want to make sound, you got to change the volume of the fluid. And so it takes a much stronger, it takes vortical disturbances of much higher amplitude interacting with each other, and you get just and if you've taken a turbulence class, you assume incompressible, right? How many of you have taken turbulence? You assumed incompressible, right? Which is 99.9999% right. But it's that 0.0001% that's not right that makes sound. So if you want to know the sound made by a turbulent jet, you got to include that teeny weeny little bit of compressibility in that Mach 0.05 jet. This is why aeroacoustics is such a hard problem, is because you can have a flow that's essentially incompressible, but it's just that tiny little bit of deviation from compressibility, how two vortices interacting with each other slightly compress the fluid. That launches sound waves that then propagate away and blow your ears out from the airplane engine. But that is just one simple example of how, that's this example, how large amplitude vortical disturbances generate sound waves. But there's lots of other ones. And they're in my textbook where you can have two acoustic waves interacting with each other. Or you can, but basically, you get lots of other interaction mechanisms because of nonlinear processes. Okay, anyone have any questions? All right, so what we're going to do now is we are going to, I think that we're not going to talk about disturbance energy more specifically, and we're going to move to our last topic, which is, all right, what happens when these disturbances hit flames? What happens then? Yeah. Yeah, actually, I told you that I would tell you that data that I showed you from Jackie O'Connor, that transverse wave excited a vortical disturbance, and that happens because of gradients in the mean flow velocity. So an acoustic wave propagating through a region of a velocity gradient excites vorticity. So that's where that came from. You cannot, but you could not understand that problem. That's called a receptivity problem, by the way. You cannot understand that problem by saying, assume uniform mean flow velocity. You gotta model the gradient in the base flow velocity coming out of that jet. All right, so now we're going to talk about, we've talked about how disturbances arise and propagate and interact in flows. Now I want to spend the remaining time with you just doing very quickly talking about, well, how do they interact with flames? What happens when you bounce these different kinds of disturbances off of flames? This is a super interesting topic. This is what I spend my nights and weekends working on this. It's really interesting in a strange way. But I specifically am going to be talking about how flames respond to harmonic disturbances. So the whole field of turbulent combustion is how flames respond to, things that are not time harmonic. But this problem is complicated enough. But at least it'll kind of give you a feel for some of the key drivers here. And let me just jump ahead. For example, this shows you data that kind of motivates this problem. Is in the problem of combustion instability, one of the things that we always need to know is what's the sensitivity of the heat release to velocity disturbances. So that's that whole feedback loop. And we need to know a quantity. I kind of waved my hand and told you, and I showed you a movie that shows you that flames are sensitive to velocity. But I need to quantify that. And I need to quantify both the gain of that, but also the phase response, because depending upon the phase, that totally changes the answer. So for example, this right here shows you data where we forced the flame with velocity fluctuations. We took a speaker, just like that data, and we excited the flame with a given frequency, and then we measured the fluctuating heat release. So we measured the heat release where we inferred the heat release from the chemiluminescence, OH chemiluminescence coming off the flame. So that's capital Q prime. And then, so U prime is the fluctuating velocity. U naught is the mean velocity. And that's my input. And then the y-axis is Q prime, normalized by Q naught. And so, I could hit the flame with 10% of the mean velocity or 20. In fact, I ran it all the way up to about 70 or close to 80% of the mean velocity. So the slope of that curve is like the gain, right? It's how sensitive the flame is to disturbances. So, and you can see the gain is somewhere around, the normalized gain is somewhere close to 1 in this case, right? For example, a 0.2 fluctuation in normalized fluctuation in velocity gives me somewhere maybe just a little bit above a 0.2 fluctuation in heat release. And similarly, and so, let's see. What happened there? And then what I can do is that slope there, if I call that the gain, the gain of this is a transfer function. I can plot that gain as a function of frequency. And so this is data, not measurements, but data looks just like this. So here the x-axis would be a normalized frequency, just showing you how that gain varies with normalized frequency. And so, questions like, well, what factors affect the slope of this gain? Why is it 1? Why is it oscillating? Why is it dropping? Why is there a node there? Those are all really interesting questions. That's kind of the linear world. But then also, this thing doesn't continue to grow linearly, right? If it was linear, the input-output relationship would be constant. But it saturates in this case. And it turns out that that saturation is hugely important to understanding why, if you have an instability in a rocket and you want to know why it's just a minor annoyance versus blows the whole thing up, it comes down to what amplitude it saturates at, because that's going to control whether the instability in the rocket is tiny, medium-sized, or just massive. But questions of why is it saturating? Why is it saturating at an amplitude of 0.45? And why is it saturating at a velocity of 0.4 and things like that? These are really tricky problems, but this is some of the kinds of questions that we're asking. And this is just the sensitivity of the flame to velocity disturbances. We also, for other problems, you want to know what's the sensitivity of the flame to entropy disturbances or to vorticity disturbances. This is acoustic velocity disturbances. All right. So I'm just going to jump over this stuff because we're not going to have time to go through all the details. But we're going to particularly look at premixed flame dynamics, and we're going to use something called the G equation, which I'm going to come back to it, but I just decided not to. I want to show you some data before I show you equations. So let's start by we're going to think about premixed flame dynamics, and there's some similarities between premixed flames and dynamics, but there's also some significant differences between premixed and non-premixed flame dynamics. So I'll spend most of my time talking about premixed flame dynamics. But here I have a bunch of images. This is data taken by Santoshi Anbo, who's at MIT right now. And these are data where I have this bluff body just to stabilize the flame, flow's going up, and the flow's seeded with olive oil, so the olive oil burns. You get a nice, smells like an Italian kitchen. I'm running this experiment. The olive oil's burning, and it disappears, and so we shine a laser through it, and so the kind of gives you an idea of where the reaction sheet is. And then that top left image shows you, kind of the flame without any imposed acoustic excitation. And it bounces around. You've got inherent disturbances in the room. But then as we start adding velocity fluctuations, you can see this. And so I think let's see if these videos are going to work. So there it is. Acoustic wave bouncing up and down, and it's exciting the flame. And so put that repeat on it. So a couple things that you can see going on here. First of all, you get wrinkles on the flame. And they're pretty short wavelength wrinkles. Although I'll just tell you, I'm exciting this flame with a really long wavelength acoustic wave, much longer wavelength. But the flame wrinkles don't track the wavelength of the acoustic wave. They're a lot shorter. You can see that these wrinkles are clearly convecting. They're moving downstream. And then if you were to measure, at a fixed location, how much is the flame flapping around, you'd clearly see the flame's oscillating. It's moving around. So that's that lower amplitude case. So if I double the amplitude, you see a lot of the same observations, just the wrinkles are getting bigger. And if I go to the really much bigger one, what you can see now, actually you can get a little bit of insight into what's going on here is that this flame is clearly exciting the shear layer that the acoustic wave is clearly exciting that separating shear layer off that bluff body. And there's vortices in the flow. And you can clearly see how those vortices are spinning around and rolling up the flame and interacting with it. These same vortices were here at the lower amplitude, but you don't see them. And what that's telling you is it's important to realize that this is not flow visualization. This is flame visualization. The flame is not a passive scalar. It's not following the flow, right? Flames do two things. Premixed flames do two things. They propagate normal to themselves, and they also move with respect to the flow. And so if they didn't propagate normal to themselves, we could watch what that interface was doing and see what the flow is doing to the flame. But because the flame is propagating normal to itself, it's doing its own thing. And remember, flames propagate normal to themselves at the flame speed. And so if the fluctuations in velocity are smaller than SL, if U prime is smaller than SL, that propagation of the flame normal to itself is really, really smoothing out, and it's really distorting what the velocity is doing to it. Yeah? Oh, this is totally, well, the acoustic wave is exciting the Kelvin-Helmholtz instability of the shear layer. It's absolutely what's going on. Yep. But my point is that, again, this is not flow biz. It's just that what you're seeing is how the Kelvin-Helmholtz instability that's excited by the acoustic wave, it's synchronized to the acoustic wave. It induces velocity fluctuations that are moving the flame around, but then the flame is also propagating normal to itself, smoothing itself back out. And you're seeing the superposition of both of those. Okay, so those are just some images of what this thing looks like. Here's another set of images. This is a much more complicated flow. This is a, oopsie. See if this one will play. These are OH PLIF images. So you're taking a slice through a really three-dimensional flow. Flow's going left to right. It's an annular flow. It's swirling, so you've got all kinds of different shear flow instabilities and so forth. And so if you're not used to looking at these images, let me just quickly orient you. So what you're looking at here is the OH radical, which is post-flame, and it's super equilibrium at the flame. And so where you see the dark blue is where the reactants are, no OH radicals. So this is where the reactants are. This is unburned reactants right here. Unburned reactants here. And then when you start seeing all these colors, that's post-flame combustion gases. And so the interface between all these colors and that dark blue is where the flame is. And so, this one's a really cool one. You can see that big old vortex spinning around. It's this flow is going about 60 meters per second. So this vortex is strong enough to take a 60 meter per second flow, whip it around, and send it back the direction it came from. And the acoustic, and what's happening is that is a Kelvin-Helmholtz instability interacting with shear flow of this shear layer that was excited by the acoustic wave. But it grows, and it becomes such large amplitude that it just becomes huge. You can see another one here. The whole flow is oscillating. That's why, here the flow is really shot out. So the reactant jet is way out there, whereas here, almost flashed back. The flow is almost reversed. You just see a tiny little bit of reactance there. You see, in addition to that, you can also see these nice little shear layer instabilities on both the inner shear layer and the outer shear layer. So that's another one. Here's a bunch of other ones. Oops. See if I have these videos. Oops. Nuts. Oh well. Okay, but here are some videos. Just a bunch of different conditions. This is line of sight chemiluminescence now. So you're integrating across a 2D domain, all the light given off of it. The white line I've dropped on to kind of give an idea of where the instantaneous flame edge is. And this is the preheat temperatures varying between 294 and 866 K. Actually, I don't know if you remember yesterday where I talked about how as you go up in preheat temperature, the gas expansion ratio of a flame changes. So notice the fundamental change in what the flame's doing on the far right and on the far left. Both of these are getting excited by an axial acoustic disturbance. Over there, it's exciting this Kelvin-Helmholtz instability of the shear layer. On the right, notice you get this sinuous von Karman street-looking thing. And so actually, the dominant fluid mechanic flow instability is changing because of the gas expansion, major gas expansion difference across the flame in these two cases. But that is not the purpose of what we're talking about here. So anyway, these are just four different conditions. And what I've done here is I've just overlaid a bunch of those instantaneous flame edges so you can kind of see what's going on. And one of the things I'm going to look at a little bit more detail a little bit later is particularly this far left image. If you look at all those instantaneous images, in turbulent combustion, we call that the turbulent flame brush. This is obviously more than just turbulence, but just kind of the overall region of flapping of where the flame is, you call the turbulent flame brush. And in turbulent combustion, the turbulent flame brush grows monotonically with downstream distance. Okay, standard classical observation, et cetera. It's a little bit, there's more going on, a little bit like this right image here. Kind of interesting though, if you look at that far left image, you actually see this brush, it starts narrow, it grows in width, and then it actually decreases in width. And so that's pretty interesting. You don't see that if we were thinking about sensitivity of flames to just broadband turbulence, you wouldn't see that. And we're going to talk about where this is coming from a little bit later. You can also see in all the cases that the amount the flame is flapping starts out really small. And that's due to flame attachment or flame stabilization. So we talked a little bit about flame stabilization yesterday, but it turns out that flame stabilization has a huge impact on how flames respond to disturbances. And you can kind of visually see it here, right? They all start small, and then they're going to do something else, but they're starting at the same point, at least in cases where the flame is tightly attached. So you can disturb the flame saying, you can disturb me, you can knock me around, but my anchoring point's going to stay pretty fixed, pretty rigid. So there's that. Okay, so now I want to get a little bit more quantitative. So this is some of that same data that I showed you first. I just turned the image sideways. Flow's going left to right. And what I'm going to do is I'm going to quantify how much the flame's bouncing around. All right? And I'll call that L. And I'm going to apologize because I think this slide in some spots calls it L and other spots calls it zeta. But I'll tell you when I do it. And L is a function of x. It's a function of t. Okay? And so I want to quantify that. Well, I can extract that from these images. And so, top right, that's one of the time series. L's bouncing around in time. You can kind of see it with your eye. This just quantifies it. I can take a Fourier transform of L. And I was exciting this flame with 300 hertz. And sure enough, it's flapping around and oscillating at 300 hertz. So you can see that. That's one position. What I can also do then is I can plot what that spectrum looks like at different spatial locations. So that's the plot. So now what I've done is I've added another x-axis. This is how much the flame is flapping around, L prime. This is frequency. And I've normalized it by the forcing frequency. So it's peaking at 1. And this is downstream distance. And I've normalized the downstream distance by that convective wavelength that we've talked about, which turns out to be really important for flames. And so that's at another spatial location, and that's another location, and that's another location. And so you see this peak, you see this nice narrowband peak, you see it actually grows, you see it drops. You can also kind of see that the level of background, there's broadband background, not much here, but this whole background has come up. That's just inherent turbulence in the flow causing more random broadband wrinkling in the flame. And then what I can do is I can grab the envelope of that curve, look something like that, and you see this strong response at the forcing frequency. You can see it's non-monotonic. And that kind of reminds us of what we saw when we looked at this flame brush, is the magnitude of, these are same idea, just I plotted it in different ways, is the magnitude at which the flame is flapping around. It's growing and then it's decreasing. Okay, so now what I've done is I've just, since it's all the interesting, or a lot of the interesting action is just happening at one frequency, I'm just going to take this curve and I'm going to get rid of this axis, the frequency axis, and I'm just going to plot the magnitude at the forcing frequency. And so that's this, the magnitude of flame flapping as a function of downstream distance. And a reminder, this is the magnitude at which it's flapping at 300 hertz. So it's oscillating at any given point, flame's flapping up and down, bouncing around. But the magnitude at which it's bouncing up and down is changing with space. But I haven't talked about it before, but this is the phase of that flame flapping. All right? And you can see the phase rolls off monotonically with distance. And whenever you see a phase that varies linearly with distance, that means you have a disturbance that's moving at a constant speed. Because, I don't know if you guys are going to be able to see this, but remember, for example, I had a disturbance moving at constant speed is e to the I omega x over ux naught. We talked about that before. Well, that is, and then we had this multiplied by e to the minus I omega t. So I can write this as e to the minus I omega t plus a phase, which is a function of x. And that phase, which is a function of x, is equal to omega times x over ux naught. So notice the phase varies linearly with x. So in fact, the slope of that curve is going to be proportional to omega times whatever speed that wrinkle is moving on the flame. And since I know frequency omega, I can actually, from the slope of that line, exactly extract the phase speed of that flame wrinkle, how fast it's moving down the flame. But that's what that means. And remember the images. We could see those wrinkles moving down the flame. This just quantifies it. So just a couple quick observations. So again, low amplitude fluctuations near the attachment point. They grow downstream. They peak, not sure why. Then they drop off. They decay. And you get this approximately linear phase frequency dependence. So that's just one case. And here's some other data. This is from another condition. This is L prime as a function of downstream distance. And you see similar idea. It grows and then it decays. But you can also see a smaller wavelength modulation on top of that. We'll talk about what's going on there a little bit later. Over here, this is a really interesting one. You can see multiple modulations of the flame wrinkling amplitude. So what this means is, if you're looking at flame flapping, the flame is really flapping like crazy here. But here, it's not flapping around much at all. And here, it's flapping, and here, it's not flapping. So again, we'll talk about what's going on with that a little bit later. So to deconstruct what's going on, there's really 4 key things that are going on, and we're going to tackle them in successive order. And that is just some basic flame dynamics. Is similar to what we talked about this morning. Is once you create a wrinkle, what does the flame do with it? If you perturb a flame, you just pop it, you just move it over, what does the flame do with it? Then we're going to talk about, well, how do you create wrinkles in the flame in the first place? Where do they come from? And then we'll talk about interference and destruction a little bit later. So in order to tackle this problem, we need some equations for the space-time dynamics of the premixed flame sheet. And this is all that stuff that I just shot over where I derived this equation. How many of you have seen the G equation before? OK. Did you do that in Heinz Pitch's class or this week? OK. The G equation is an equation that describes the space-time dynamics of a surface that propagates normal to itself, which is what premixed flames do. So, and it's a nonlinear partial differential equation. So L denotes the flame position. U and V denote the velocity at the flame. The subscript F means, remember, the velocity is a field variable. It's everywhere. The flames don't care about what the velocity is everywhere. They care about what the velocity is at the surface. So that's what the subscript F is. SL is the flame speed. So in essence, the left-hand side here just describes how the flow is pushing the flame around. The right-hand side describes how the flame is propagating normal to itself. And you get this really nasty nonlinearity. This makes analytical analysis of this problem really hard. And this is basically this geometric nonlinearity that says, as you wrinkle and perturb flames, the flames just keeps propagating normal to itself. If you wrinkle it this way, it goes that way. If you go that way, it goes that way. But it's propagating into the reactants at the speed of SL. OK, so that's the analytical equation we're going to be using for a lot of this analysis. OK, so let me do a little model problem for you now. And let's say that I have, you can never do this in the real world, but you can do it with a computer. Let's assume that the velocity is everywhere equal to UA for time less than 0. And then at time t equals 0, I make it everywhere equal to UB, OK? Instantaneously. And UA is constant everywhere, and UB is constant everywhere. So the only way this could actually work is if this flame doesn't generate heat release. It's just a surface because otherwise the flow would accelerate through the flame. All right, and then I have this flame holder, that little black dot in the middle. And so the angle that flame makes with respect to the reactants is basically going to be, you have sine theta equals UA over SL or SL over UA, right? Just what you learned about in Combustion 1 classes. Steady state, the flame, premix flames have this really interesting feature is that they can set up a steady state. If you give them a stabilization point, they'll propagate into the reactions, and they set up this angle. But then the question is, okay, so now UB is going to be bigger than UA, and so the flame will find a new steady state where the flame will be at a steeper angle. But the question I want to ask you is, how does it go from UA to UB? It starts out like this. For given enough time, it's going to look like that. But how does it go like this, or how does that happen? And so this video. Oh, bummer. Oh yeah, there it goes. Cool. Shows you what happens. Do it again. And what you can see is at time t equals 0, you get a step change in angle, and then that change in angle just moves downstream, and then you get that new shape. And so, and this just breaks that down. But basically, it's essentially like a shock wave. But basically, you get this wave, which is this discontinuity in angle of the flame that moves downstream along the flame in the flow direction, and it actually has a pretty well-defined speed. And the way to figure out that speed is from the following geometric construction. So forget about what's on the left for a minute, but we have a flame. You have the mean flow velocity U0 going in that direction. The flame is propagating normal to itself at the speed of SL. So if we take the vector combination of U0 and SL along the direction of the flame, we get this new speed, which I've called UT. And UT is the speed with which wrinkles move on flames. So, which is not U0, it's not SL, it's UT. And in fact, if I'm making a measurement, and so the axial, if I were to project UT, if I were to say what is its component in the flow direction, it's UCF. And so you can see that UCF is going to be less than U0. So what this means is, again, we've talked about acoustic and vortical and entropy disturbances. Now we're talking about flame disturbances, is that if you have a premixed flame, a flame sheet that propagates normal to itself, if you perturb it, it's going to wash that perturbation downstream at the speed of UT, which is less than U0. And so what this means is that the mean flow speed is not the same as the wrinkle convection speed. So this is actually data that we measured, where we measured the different velocities. And so the mean flow velocity is, well, that would be 1. The convection speed of the flame wrinkle is actually changing with distance. But I extracted this from those phases that I showed you earlier. Remember I showed you how the phase of the flame wrinkle, you could extract a velocity. And notice that the speed with which the wrinkle is moving along the flame is not equal to the mean flow velocity. We're going to get into this one a little bit later, but you also had that Kelvin-Helmholtz instability. You had these vortices, which you could clearly see moving along the flame. Turns out that they're moving at their own speed. I can extract that from PIV. So these black squares is that. And so you have this, when you're looking at these flame dynamics problems, you have this interesting situation where you have these convecting vortices, which are excited by the acoustic field. They're exciting the flame, they're wrinkling the flame, they're moving at one speed. You have the flow velocity, another speed, and then you have the speed with which the flame is moving those wrinkles along its surface, which is another speed. So you got 3 reference velocities when you have these premixed flame dynamics. By the way, that doesn't happen with non-premixed flame dynamics. Since non-premixed flames don't propagate, the speed with which wrinkles move along non-premixed flames is just the flow speed. Okay. So one other thing I'll just say is if we go back to this problem here, is this is a classic experiment where they took a bluff body and they just shook the bluff body. No flow disturbances at all. Okay, the flows, well, the bluff body might have disturbed the flow a little bit. They disturbed the bluff body, but you can see that creates, and as you disturb the bluff body, you move the flame, and you can see those persist all the way downstream because the flame is just, it's doing whatever it's doing, and it's just convecting that downstream. If you took this, the G equation though, that we talked about, and you actually looked at this problem of an oscillatory bluff body, you could actually and solve for, hey, what's the space-time magnitude of flame wrinkling? Here's where I switch notation on you. Zeta prime is the same as L prime. If I take that bluff body and I neglect those nonlinear terms, I shake the bluff body and I say, what's the magnitude of the wrinkle with downstream distance? That's your answer. Pretty boring. The magnitude of the wrinkle is constant. So you create this wrinkle in the flame. The wrinkle convects downstream. So if you look at the phase rolls off linearly with a speed of UCF. So the phase rolls off linearly. You'll notice that it's not the same as the mean flow velocity, but with constant amplitude. But all right, so that's just kind of a reference case. Now I want to talk about where those wrinkles come from. So if you take that G equation and you solve it, all right? And now in order to solve it, I actually have to linearize it. All right, so I'm going to jump over that step of linearization. And it turns out it's, rather than looking at the flame position, L or L prime, it's a little bit more intuitive to look at the slope of the flame. So I'm going to show you the solution for dl prime by dx. So this is the linearized. Jumping back here real quick, make sure we're all on the same page. The linearized solution to that equation, assumed just like what we did before, U equals U naught plus U prime, L equals L naught plus L prime. Solve it for L prime. And this is the solution that you get for dl prime by dx. Notice it has two terms. Let me skip over all these animations because you guys don't have them anyway. So first of all, notice that in both you have un prime. So un prime is the fluctuating velocity normal to the flame, which I've illustrated on this plot here. So the velocity is a vector. The flame doesn't see vectors. It sees scalars. It sees what's wrinkling the flame is whatever is normal to the flame is causing it to wrinkle. So un prime is showing up there. You can also see these convection operators showing up for real. So notice we have t minus x on ut there. So that's that velocity, the mean velocity along the flame. So the flame cares about the fluctuating velocity normal to it and the mean velocity tangential to it. Because the fluctuating velocity normal to it is what excites a wrinkle, and the mean velocity tangential to it is what convects that wrinkle once you excite it. So here you see that t, remember, look at how space and time, they only show up together as t minus x over ut. Or here we actually have a convolution integral, so it shows up there. But that's the wrinkle convection. It can be seen right there. So to start, let's just say we want to understand where those flame wrinkles come from. So let's assume that we have a spatially uniform disturbance field just to start on, okay? Which means that this term goes away because it's a gradient. So we only have that term right there. And so notice that this term is proportional to the fluctuating velocity at x equals 0. All right? So that's interesting. What's happening here is that this problem is completely controlled by flame attachment. So I didn't tell you this, but I solved this problem subject to the boundary condition that L prime equals 0 at x equals 0. I said the flame, even though the velocity is bouncing around, the flame is attached. It's not moving at x equals 0. And that leads to this term right here. So in other words, flame attachment actually leads to the excitation of a wave at that attachment point. And so what's happening here is that's flame attachment. Imagine think about the angle that the flame makes with respect to the reactants. The reactant velocity is oscillating, so the flame angle is oscillating. And then that oscillatory flame angle just keeps getting convected downstream at a speed of ut. And just to see that, I have here a video. This is data, actually. This is a movie. These are little pilots just so the flame really locks the flame down. And you're looking at the base of a flame that's oscillating. So you see the oscillatory angle of the flame, and then if your eye can do Lagrangian things, just you can kind of see the angle stays fixed as it convects downstream. So at a fixed location, the flame angle's oscillating. But you can also just kind of convince yourself that you can track a surface where the flame angle's staying constant, which is just the angle at the base of the flame's oscillating, the flow is just convecting it, washing it downstream. So this one is this is an interesting point because it says that, in the limit where your excitation velocity is spatially uniform, flame anchoring completely controls the problem. And so this is kind of a limiting case where the flame doesn't move at all. If the flame bounces around a little bit, the problem would look a little bit different. And so, we haven't talked about kinetics or diffusion or heat losses to burners. But although those aren't explicitly shown, those show up in what I'll call that boundary condition, is what's the flame doing at x equals 0? Is it bouncing around or does it stay fixed? Just going to jump over this. And so, we talked about this earlier, but this is a whole bunch of different data sets showing the magnitude of flame wrinkling as a function of downstream distance, and they're all starting near x equals 0, again, because of attachment. So flame anchoring, flame attachment, super important process to understand flame dynamics. Okay, now I want to think about a little bit more interesting problem, which is where the velocity field's not uniform. Because in reality, for example, we could see those convecting vortices, and those convecting vortices clearly have space-time variation. And so dun prime by dx is going to be non-zero. And basically what's happening here is, remember, what's wrinkling flames? It's un prime. So if un prime has one value here and a different value here, that's actually going to change the angle of the flame, right? If the normal velocity is equal everywhere along the flame will stay flat. But if I have a normal velocity which is really big here, it's going to push the flame, whereas if it's here, it's small, it's not. And so you cause fluctuations in flame angle wherever you have fluctuations in the normal velocity, which kind of makes intuitive sense. And so remember, that fluctuating velocity is coming from these convecting vortices that we could clearly see. And that, here this is that data I showed you earlier. And the black filled square is the speed. And so what we have here is we have a situation where the flame is getting perturbed by a vertical disturbance moving at the speed of what I've called UCV. It creates a wrinkle in the flame, but then that wrinkle in the flame then convects at that speed of UCF or UT, whatever, which depending on your coordinate system. So that's kind of interesting. The other thing you can see here is this is a convolution integral. So if you want to know what the flame is doing at a position x, you have to know everything from 0 to x. All right? And I want to spend a minute talking about this because this is really important, especially for those of you who might be working in turbulent combustion. Flames are not local. So if you want to know what's causing flame wrinkling and flapping at a given position, it's not just a function of what's happening at that position. It's a function of everything upstream of that position. Why? Because of this wrinkle convection we talked about. Is that if you disturb a flame here, it's going to convect that wrinkle, and it's going to create a wrinkle here as well. Even if I only excite the flame at the base and create a wrinkle, you'll still see wrinkles everywhere because those wrinkles get convected. And so imagine a situation where the flame's getting disturbed everywhere, and I want to know what's happening here. That's going to be a function of everything that happened upstream at an earlier time. And that's the t minus x prime over ut, the convolution integral. So flame disturbance at location x is a convolution of disturbances at all upstream locations in previous times. So it's non-local in space. It's non-local in time. And I just see so much, the reason I want to emphasize that is there's, a lot of these turbulence closures and things like that are essentially local models, is that you assume that turbulent flame speed at a given point is a function of the turbulent velocity at that same point, rather than realizing that what's the turbulent flame brush at a given point is going to be this convolution of everything upstream. Okay, and then this second bullet just says what I just said, is that where do these UN primes come from? In many cases, they're coming from vortices that are convecting along the flame, but they're moving at a speed that's different than the speed of the wrinkle. And we've already kind of talked about this before when I showed you that data where I said, what happens if I have two disturbances moving at different speeds? So here we have another situation where we have a source of disturbances moving at one speed, and we have a flame wrinkle that's moving at another. So in order to understand this, let's do a model problem. Let's say I have a flame. Let's excite it with a convecting velocity field. So here I have a UN prime, and it's going to be excited by a disturbance at a frequency of f, and it's going to be moving at a speed of uCv. All right? What will the flame's space-time wrinkling be? Here I just gave you the solution. So again, here I've switched my notation. Zeta 1 is the same as L prime, or L1. So this is the magnitude of flame wrinkling, and it's all this stuff. And it looks complicated, but if you break it down, it's actually not too complicated. So basically what we have here is the flame wrinkling at a given space and time is a sum of two terms, this term and that term. And notice that this term right here, you see UCV. This term right here, you see that UT, or here I've called it UT naught. So basically what you're looking at here is the interplay of a disturbance moving along the flame at a speed of UCV, which is that vortex that's exciting the flame and keeps exciting wrinkles. And then also just the flame's natural, once you create a wrinkle, the flame is convecting that wrinkle at a speed of UT naught. I just gave you this so you could see where it comes from, but if you plot it, if you plot this thing, and you plot the magnitude of flame wrinkling, this is the same as this plot. This is this model problem. It's not reality. Reality is much more complicated, but it gives us some nice vocabulary and intuition. The y-axis is basically what we were calling L prime before. I showed you all that data of magnitude of flame wrinkling as a function of downstream distance. And notice what you get. Starts at 0, flame's attached, it grows, peaks, goes to 0, goes up, comes back down. And so what's going on here is, again, it's like that interference pattern that I was talking about earlier, is you've got these sources of disturbances of flame wrinkles, and the flame is convecting those wrinkles. They're interfering. Some points they're in phase, some points are out of phase. And so even though the flame is being disturbed at all points, they actually cancel each other at this location right here. Flame's not moving at all. It stays fixed, whereas here you get this big amplitude. And in fact, you get a new length scale with this problem. And that's this length scale over which you get these peaks and valleys. And that length scale, I'm going to call lambda interference, is proportional to the difference between the speed at which the vortex is moving on the flame and which the flame convects wrinkles. So notice that if this quantity is 1, if they're moving at the same speed, this interference length scale goes to infinity, right? This becomes 1 minus 1, so it's 1 over 0. It's infinity. That means there's no interference. You don't get interference. But if UT on UCV is not 1, then this thing has a value. And the farther apart these things are, the shorter that convective wavelength, that interference length scale becomes. Okay, so with that, why don't we take a quick break? We're supposed to be done at 12:15, is that right? Okay, so yeah, be back at 11:30, and we'll wrap this up.